Hey everyone, welcome back. You can see my face this time. I don't know if I'm going to leave this on the whole time, but let's get started right away with discussion 2. So, you are given that y equals 10 minus 5x minus... y equals 10 minus 5x plus 3x cubed. Okay, so that looks like this. Y equals 10 minus 5x plus 3x cubed. Okay, so if we want to find dy dx, we must first recall that y of x, if y of x is equal to x to the n, then dy of x dx is equal to n times x n minus 1 times dx dx, which is equal to 1. So dy dx is equal to n x n minus 1. So this is just a quick reminder of how to take a derivative, just in case you don't remember. So this part here you can pretty much ignore. This just means, well, this is just part of the theorem, but we don't really need it in most cases. So here, dy dx is n x to the n minus 1, right? So now let's take this dy dx of the function that we're given. So we have, let's copy and paste this. I'm going to take this down here. Okay. So dy dx is equal to, what we're going to take is the derivative of 10 with respect to x minus the derivative of 5x with respect to x plus the derivative with respect to x of 3x cubed. Okay, well, the constant 10, or any constant for that matter, is not a function of x, so we can just get rid of that. That goes to 0, right? And we're left with, next is going to be negative 5 plus 9x squared. Yeah, so our answer is C. Okay, moving on. Next problem. D2. Let's just go down here. D2, because I have the graph, so this is going to make it a little easier. Okay, so you can find this in your textbook on page, it tells you here, page 55, problem 33. So that's what it looks like in the book. Interestingly, this tells you that this is page 55, problem 33, but that is not what it says on the sheet. At what time is velocity particle equals 0? Yeah, it's almost the same, but apparently there's a discrepancy here. So if we look here, it's got t of 150 to t equals 450, and in the book it says t of 1 to t of 350. Maybe I have a different version. I don't know, but I'm just going to go with what's in the. I'm going to go with what's in the worksheet. Okay. Average velocity of the particle during the time interval t equals 1.5 seconds to t equals 4.5 seconds. Express your final answer in vector form. Okay, so well, we need to look at this graph, and we need to look at time interval. Time is equal to 4.5, right? So that's down here. 4.5 seconds, right? So here, this is where our y value is. We need to figure out what is that y value. Okay, well, we have 16, 17, 18. Now if I zoom in a little bit, you can see that the line actually falls between 17 and 18. 16, 17, 18. The line falls between these two values. So I'm going to say that that's 17.5. Okay, now next we are going back to 1.5 seconds. So 1.5, we have a value here, our y value is here, right at, let's see, this is 8, 9, 10, 11, 12, so this is 11. Okay? So what we want to do to find the average velocity is we want to take the change in y over the change in t. This is going to give us average velocity. Okay? So let's do that. We have up here, what did we have? This was, let's make that red so we can read it. 17.5. So the change in y is 17.5 meters minus 11 meters over the change in time is going to be 4.5 seconds minus 1.5 seconds. This is going to give us dy delta y over delta t. Okay, this is going to be, what do we have? We have 6.5 meters over, this is actually 4.5, not 14.5. That looks kind of hard to read. 4.5 minus 1.5 is 3 seconds. Okay, this gives us a value of what do we have? Oh, it's 2.2. Let's say it's just 2.2 meters per second. I did a little bit of rounding there, but that's going to be our value. This is average velocity. So here's the answer, given what we have on the worksheet. If you did this for the problem in the book, it's going to be different. So just be aware of that. Our values are not the same as what is listed in my book. So that's something to think about. You might even want to try it on your own. Okay. Part B. Using the tangent to the curve as shown as the orange line in the figure, what is the instantaneous velocity of the particle at time equals 1.5 seconds? All right. So here is our tangent. Oops. Get rid of this stuff so we can see it. Right, here is our tangent, this orange line. That's tangent to 1.5 seconds. 1.5 seconds is right here. So this is parallel to the value, to the y value at 1.5 seconds. We want to know what is the instantaneous velocity of the particle at 1.5. Oh, what is the slope? That's what it's asking. So what is the slope of this line, this orange line here? Well, we can do that by taking the rise over run. If you recall from y equals mx plus b, the equation for a line, that m is your slope, and that's equal to rise over run. So in this case, we have a value. This is going to start at 0, 1, 2, and then we have up here, it's at 20. So from 2 to 20. So rise is 18 because we start at 20 minus 2, right? So we go up 18. So rise is equal to 18. What is our run? What is the x value? We start at 0 here, and then we end up at 3. Right? I don't know if you can see that. I'll make this a little more clear. So this is our rise. This is our run. Okay? So again, from 0 to 3 and from 2 to 20. Okay? To make it more explicit, I'll just do this. 20 minus 2 over 3 minus 0. Okay, that's going to give you 18 over 3 equals 6 meters per second, right? Because this was meters. I should have put my units here. Now we can see it more clearly. So the instantaneous velocity of the particle at 1.5 seconds is 6 meters per second. So 6 meters per second is our answer. Okay? To make it a little more clear, I should just write v. Okay? All right, next. At what time is the velocity of the particle equal to 0? Well, if we go to our graph, what we're looking for, so recall that the velocity is the change in y with respect to t. Y is our position. So our velocity is going to be the slope at any given point, the slope of the tangent at any given point, and we're looking for something with a slope. We're looking for a tangent with a slope of 0. That's what we're really asking. So right here, we actually have that. So at what time is this? I would say it's, let's see, I'm going to go ahead and zoom in. I'm going to say it starts, 0 is really about right there, which is going to be about 3.75. That's what I would say. You could also say it's at 4. Yep. I'm going to go with 4. It's actually both. .75 is really my answer. That's what I would say. And I would argue for that. That's when the tangent is equal to 0. Okay? But recall, if you're asked to be, if say you're doing this on WebAssign and it comes up wrong, I would try a couple of different values. I would try 3.75, I would try 4 first, and then see what happens. Okay, next problem. The position in meters of a particle moving along the x-axis is given by x is equal to 25 minus t minus 5 all squared, for t is greater than or equal to 0, where t is in seconds, of course. Because we can never have any negative t when we're talking about physics. There is no such thing as negative time in basic kinematics. Okay? Sketch a graph of this function before trying the questions below. Okay. Going here, we're going to say this is D3. Okay. So we have a function. X is equal to 25 minus t minus 5 all squared for t greater than or equal to 0. Right? This is time. Time is in seconds. Okay. And it wants to know, okay, first we have to sketch a graph of this function. All right. So we need to find where this thing goes to 0. Let's first draw an axis. Okay? Let's draw axes. This is x of t up here. This is going to be t in seconds. Okay? Now, we know that it's going to be somewhere up here, shifted up by 25, because we have the constant positive 25. So let's call this 25. Okay? We also know that x is going to be 0 when this value is equal to 25, because we have 25 minus 25, right? That means that t would need to be 10. So what I'm saying is this, 25 minus 10 minus 5 all squared. This is equal to 25 minus 5 squared, which is equal to 0. Okay, so x is going to go to 0 at 10 seconds. Okay, so we have that. Let's go here, say 10. Leave that there. All right, what else can we say? What happens at t is equal to 0? We have negative 5 squared. So x is also going to go to 0 at that point. So we have 25 minus negative 5 all squared. That's also equal to 0. Don't believe me? Plug it in. Okay. All right, cool. At t is equal to infinity, if we're taking limits, why not? Let's try it out. Let's take t is equal to infinity, 25 minus infinity minus 5 squared, by the way. Well, that's just going to be negative infinity, right? So we got limit of as t goes to infinity here. That's what I'm really saying. This was x. This was x of... Oops, sorry. This was x of 10. This was x of 0. I think we actually need to solve this anyway for a later part in the problem. Okay, so we've learned a little bit about the behavior of x, right? We know it goes to 0 at t equals 0 and at t equals 10. Okay, cool. We're almost there. We've almost got it. Okay, so I'm trying to... my goal here is to take it slow with this type of thing because sketching curves becomes very important if you pursue especially physics, but I'm sure in other sciences such as engineering it's also going to be pretty useful. So this is what we have so far, and now I want to point out that in x we have this. We can say that t minus 5 is some other variable, right? Let's just redefine it for 1 second. We're going to go, this won't be a lasting thing, but I'd like to just point something out. We'll call it alpha, right? So now we have as x is equal to 25 minus alpha squared, okay? And this is x of alpha. Now, because we've made a substitution, okay? So in this, right, we have, from our graph, we've already pointed out that we're going to be shifted up by 25. We're also going to be like negative. So this is a quadratic form, and it's going to be negative. So that's really my point here with alpha, is that this is going to be an upside down parabola. So now let's just sketch it. We have everything we need. We can just get going. Let's not take all day on this. Okay, so I'm going to move this line down because I'm not great at drawing, and I just don't want to have to deal with erasing this a million times. So let's say our function's going to look something like this. Well, that's about the best I can do as far as actually drawing the thing, but the math is all pretty much there. Okay. So this is essentially what your function x should look like. We'll call this x and then write the function down because that's typically how we do these things. Okay, there you go. Next, what is the next part? So D3 is actually asking. So I feel like that part of the problem is actually that's probably the bulk of the problem, in my opinion. But again, personally, I like to take my time with curve sketching because you can get a lot of information from a really simple function like that. Okay, what is the position of the particle when its velocity v equals positive 6 meters per second? Okay, well, let's figure it out. So we need to take we need to take dx of t dt. That's going to equal, remember our constant 25 is going to go to 0. This is going to be 2 times t minus 5 times dt dt. So our velocity is v of t equals, we'll just call it 5 minus 2t. 10 minus 2t, excuse me, 10 minus 2t. Right? Okay, so that's our function. So now what we're saying is we want to know what is the position of the particle when its velocity equals 6 meters per second. So really what we need is the time. So once we're given a velocity, what is the time? So 6 meters per second is equal to 10 minus 2t. So we just solve for t. That's really all we got to do. So 6 minus 10 divided by negative 2 is equal to t. T is equal to 2 seconds. Okay, so now we just plug that into our function x. We're looking for the position. X of 2 seconds is equal to 25 minus 2 minus 5 all squared, right? That gives us 25 minus negative 3 all squared. That's equal to 25 minus, oops, that's squared. I already wrote 9. 9. 25 minus 9. That's 16. Since we're talking about position, this is going to be meters. So x is equal to 16 meters when v is equal to positive 6 meters per second. Okay, that is your final answer there. Okay, what is next? Positive. Sorry, I should have noted that your option D is positive 16. So the answer is really D. Is D. That's what you're looking for. We plug in the values t equals 0 and t equals 10. We've already done this, but I'll just do it again real quick. This shouldn't take long at all. So we just say x of 0. Recall from earlier that when I plugged in x of 0, I got 0. See that? Also, when I plugged in x of 10, I got 0. Right? So the total distance, what is this D for? The total distance between x of 0 and x of 10, take the absolute value of that because we just want the total distance, is equal to 0 minus 0 equals 0. One thing I should note here is that when you're looking at this problem, we had, recall, the function looks something like this. Right? We had, oh, oops, we had, right, something like that. Make this so we can see it. Right, where this was 25 meters. This is the halfway point between x equals 0 and x equals 10. So really, x equals 0 is only the total displacement, right? Because we start at 0, and then we end up at 0 from 0 to 10 seconds. So over the course of 10 seconds, we essentially traveled nowhere. But there is a total distance traveled. So total displacement is 0, but total distance traveled is not 0. But we can figure out what it is by looking at the halfway point. So we have 0 and 10. The halfway point of that is, of course, 5, right? What is x of 5? 25 minus 5 minus 5 all squared. This is equal to 25. So look at that. So here's what we do. We travel up 25 meters, right? Boom, that's on the first trip. On the second trip, we traveled back 25 meters. So we essentially traveled 25 meters twice, which gives us 50 meters. So the answer how much distance has been traveled between those is not 0, it's actually 50 meters. So if it were worded a little differently, this is something to pay attention to on an exam. If it had said, what is the total displacement of x, that would be 0. The total distance traveled by the particle between t equals 0 and t equals 10 is 50 meters. That's your answer for D4. That's my final answer. A, that's the answer, 50 meters. Not sure if that's better, but okay. All right, next one, D5. So I'm trying to go slow. I do welcome any feedback on how these lectures are going. This is it's sort of a new and strange thing to have to do this over the internet. Usually when we teach physics, we like to interact much more because we can get a sense of pacing for the course. So if you have any suggestions or any questions about that, please let me know via email. Okay. So, discussion 5. An object begins to move along the y-axis and its position is given by the equation 6t squared minus 5t minus 2 with y in meters and t in seconds. Okay, so there's our function. What is the position of the function when it changes its direction? Okay, well, we are given an object begins to move along the y-axis and its position is given by the equation y is equal to 6t squared minus 5t minus 2. Y is in meters and t is in seconds. Express your answers in vector form. Okay, what is the position of the object when it changes direction? When it changes its direction. So what we're given is a function y of t. Here's y, here's t in seconds. This is in meters. Right? So also, we should note that this is a parabola. 6t squared, right? Minus a linear function minus a constant. So yeah, we have essentially some parabola here. Should be actually a little lower. Let's try again. Something like that, okay? Now, what we're looking for is where is this thing going to change direction? So, well, we know from what we can just see is that this is actually going down. We're traveling downward before we hit a point right here, okay? This right here is going to be where our tangent, our velocity, is equal to 0. So right here, v is equal to 0. That's when it's going to change direction and start going up. Okay, that's what we want. So what we need to do is solve for where does v go to 0. We have a function y of t. We need to find dy dt. What is this? That's something else. Okay, dy dt. Okay, recall from earlier how to do the derivatives and from calculus. 6t squared. So we have 12t minus 5. That's our derivative. Okay, I encourage you to try that on your own if you are uncomfortable with that, or go back to the earlier part of the lecture and look at the brief theory I showed. Okay, so here we go. 12t minus 5, we want it 0. We want to know where, at what time does that go to 0? So this gives us t is equal to 5 over 12. Okay, then that's the time where velocity goes to 0 and we start to change direction. Now, okay, so let's plug that in. So we say y of 5 over 12. That's going to equal 6. 5 over 12 squared minus 5 times 5 over 12 minus 2. Okay, we gotta plug that into a calculator to figure out what is the position. So that's what we're asked. What is the position of the object when it changes its direction? So let me plug that in. Okay, so that gives us negative 3.0416 repeating. That's what I got when I plugged in t is equal to 5/12. We can also say that's about 3.042. Okay, that's the position when we begin to change directions. Okay, recall from the graph above that we were going downwards, right? We defined a 0 point on our axis right here. This is 0. We just said, we looked at some place and we said that's our 0 point. And we started traveling in that direction. We've passed that point and now we're going back the other way. Okay? Okay, so for the next part we want to find the object's velocity when it returns to its original position at t equals 0. So what we need to do to find this, here we'll take this function. We want to know what is the position at t equals 0. So that's going to be y is equal to negative 2 meters at t equals 0. That's our starting point. Okay? So now we want to know how much time has passed to get us back here. So either t is equal to 0 or t is some time that has passed. Okay? So this gives us 0 is equal to 6t squared minus 5t is equal to t times 6t minus 5. So, in order for this to be true, t must be either 0 or 5/6. Right? Because if we plug that in, we should get 0. So it's t. Let's just plug this in, times 5/6 minus 5. Yep, that's right. So this goes away, that goes away, that goes to 0. Right, okay, good. Just checking my work. That's always a good idea to do that. Okay, so we obviously we don't want 0. We want to know what is the time when it's traveling, and then how much time has passed when it gets back to the original position. So that's going to be, that happens after 5/6 seconds, 5/6 seconds, right? So 0.83, so t is equal to 0.83 seconds. That's how long it takes to get back to the original position. Let's plug that into our velocity function, because what we're asked, when I say what it wants, I mean the worksheet. What we are asked right now is for the velocity when it gets back there. Okay? So velocity 12 times 0.83. What's the velocity? What is our function? I lost it. Oh, I don't have it. Well, I got to find it. Well, that's something that needs to happen. So let's find this right now. So velocity, v of t, is equal to 12t minus 5. Okay, let's plug our time back in there, because I was just starting to do it in my head and I realized I didn't have the whole function. Okay, we need that constant. So v of 0.83 is equal to 12 times 0.83 minus 5. What does that give us? Okay, so we have 12 times 0.83 minus 5. This is going to give us approximately 4.9, and there's a bunch of 9s and a 6. I'm just going to, okay, I'll just write it out. 2, 3, 4, 5, 6. I think this is right. I mean, really, we can just write this. It's approximately 5 meters per second. That's our answer. Okay? Oh, we are also asked, before we finish up, we're almost done. We're also asked that to express these in vector form, right? So okay, so for the first part, A, negative 3.042. So part A, in vector form, y is equal to, it's actually y of t, right? No, it's not. It's position vector. We want 3.402 negative 3.042 y hat in the y direction. Okay. Also, I guess I should note before I move on that this also could be expressed as, we can also express this with our variable, our independent and dependent variable. So this actually gives us, what's the time? I have to find this. What I'm saying is that we want our vector is expressed in independent and dependent variable form. So we had 5/12 seconds right here. And then we also had negative 3.042 meters. Okay, that's part A. You could also express it as I had before. This is one way to express it in vector form. This is actually of 5/12. Okay, and then we had, what is our velocity vector again? 12t minus 5. But we ended up with 5 meters per second in the positive direction. So this is going to be, what was our time? Our time was 0.83 seconds. So v is equal to 0.83 seconds and 5 meters per second.